Pre-calc, pre-calc, pre-calc. It's Thursday, 3/16. Let us see. Can anyone remember what we're studying? Okay. This video will continue on our investigation of sequences. Alright, so sequences entertained us during class today, and we need to be prepared to go on in the study of sequences. So we were looking at numbers that were in an ordered way, numbers or expressions that were in order. So we could clearly see the first, second, third, and so forth. And then we learned that there were rules or generators that created sequences. For example, we have, say, 3n plus 2. If that's going to generate the sequence, first we put in a 1, then we put in a 2, and so on. So when I put in a 1 into this generator, I'm going to get a 5. What will I get when I put in a 2? 3, 4, etc. Alright, well that's going to lead us to a special kind of sequence. And we'll pick that up in a minute. So keep that. I'm going to come back up and grab that. So it has some secrets to share with us. And we're going to go ahead and save that for a little bit. Alright. Before we do that, I would like to talk about something. This is how we generate a sequence straightforwardly. And I want to talk another way to represent a sequence, and that is called a recursive formula to represent a recursive sequence. Alright, reoccur, recursive. So we're going to look at previous terms in a sequence in order to obtain future terms. So the most famous one is this one. Oops, that's not 11, sorry. 13, 21. Do you see how I'm getting these? What I'm doing, my lighting is not very good. What is wrong? Maybe I'm in the shadow. Hold on. Oh well, do the best we can here. Alright, so the way we get these numbers is we're given the first two, and then from there we always add these two to get the next, and then we add these two to get the next, and so on. And we could keep going. That has a special name because it shows up in nature here and there, and it's called the Fibonacci sequence. Alright, we'll look at some places where that pops up in real life, but let's learn about recursive formulas for now. And the way we do that is what we call, we start somewhere. Usually we are given the first couple terms. So this term is normally called a sub 1. I'm going to call it a sub o just because I can. Sometimes we start our sequence numbering it as this is O, 0, and this one is a sub 1, and this one is a sub 2. Well, how do you know if the sequence starts out with a sub O or a sub 1? If it doesn't say, just go ahead and start out with a sub 1. But a sub O is going to designate the first term in this sequence, and a sub 1 is going to designate this one, and so on. So, now I want to know, I'm going to make an unknown out of this, and I'm going to call it a sub k. A sub k could be any one of these terms in the sequence. But I can always get a sub k by looking behind, and this means the kth term. So, like for example, a sub 4 would be, this is a sub 0, a sub 1, a sub 2, a sub 3, a sub 4. This would be my a sub 4th term, which is a 5. So the 4th term. Or a sub k could be 9. So when it's k, it's variable. That's why we call it a variable. But that's the kind of thing that it's standing for. So I can find, in this sequence, I can find any term I want, a sub k, by adding two terms back, which is going to be designated as a sub k minus 2. So for instance, if I want the fourth a sub 4 term, I'm going to have to go back to if I want a sub 4, that means k is 4 for this discussion, then 4 minus 2, k is minus 2, becomes 4 minus 2, which is the second a sub 2. So if I want a sub 4, I've got to go back and grab a sub 2. Remember, this was a sub 0, 1, a sub 2, plus a sub, what am I going to put here? So if this is a sub k, I need to grab this one, which is 1 in front, or 1 below. So it's a sub k minus 1. Alright, so this is called a recursive formula, and it always will define the next term by previous terms. And those previous terms are indicated like this. Alright, so be aware that they are going to pop up in our work, so you'll know what these little values mean. Alright, another thing that is going to pop up, lots of pop-up ideas, is factorials. They will pop up in our generators, in our sequence generator formulas, and in other places as well. A factorial is defined, for example, as say 3 factorial. It's indicated with an exclamation point. That's read 3 flat factorial, and that means 3 times 2 times 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. So it always stops at 1, and it exists for positive whole values. So we can define n factorial as n times n minus 1, just like 5 goes to 4 and 3 went to 2. It's always 1 subtracted from n times that times n minus 2 and times n minus 3, etc. All the way down till we finally get to the value 1. So that's how you figure a factorial. They will pop up in our work like this. A sub n equals 2 to the n over n factorial. So our generator has a factorial in it. So let's see what it generates. So a generator, remember, unless told otherwise, we start with 1. So I put in a 1 here and a 1 here. 1 factorial is just 1. So we have 2 to the 1 over 1 factorial, or 2 over 1. So our first term is 2. The second one is, now we're going to put a 2 in here, 2 to the 2 over 2 factorial, which is 2. Did I write 2 to the 2? I did not. 2 to the 2 over 2 factorial, which is 4 over 2 times 1, which is 2. 4 over 2 is also 2. Alright. Took care of that. Now when we put in a 3, we get 2 times 2 times 2. We get 8 over 3 factorial, which is 8 over 3 times 2 times 1, which is 8 over 6, which reduces to 4/3. Can you get the next one for me? We're plugging in a 4 into this formula. So we end up with 16 over 4 factorial, 4 times 3 times 2 times 1, 16 over 24, which reduces to 2/3. And we could take it on further. I just wanted to show you how a factorial works inside of a sequence generator. Sometimes we're asked to simplify expressions like this. This will come up in our probability unit in a few days. It'll have like an 8 factorial and a 2 factorial and the 6 factorial. So there is a quicker way than figuring out 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 2 times 1 times 6 times 5 times so on. So there's a quicker way, and I want to demonstrate it. 8 factorial, I'm going to start writing it 8 times 7, but when I get to 6, I'm going to stop and just fill in the rest by using the factorial. So this is the same as 8 factorial. Why did I stop at 6? Because I had my eye on the prize on the bottom. And now I see 6 factorial over 6 factorial. And that leaves me 56 in the top. And it leaves me a 2 on the bottom. So that gives me 28. Alright, so that's a quick method for using factorials, simplifying them. Alright. The next thing we're going to look at is summation notation. This is called summation. Summation notation. It is a Greek sigma, letter of the alphabet, and it's used for summing things up. For example, here's how summation notation is used. I'm going to have a counter, and I tell you where the counter starts. It does not have to start at 1. This one does. And at the top of the summation, I tell you where it ends. Beginning and the end. Inside or beside the summation is the typical element. Say it's 3i. Alright. If this counter appears inside, it will increment by 1 from 1 to 5, adding as we go. For example, I'm going to put a 1 in for I, and I get 3, plus, this is a summation, it's always adding things. Now it increments to 2, 3 times 2, which is 6, plus, summing as we go. We did 1, we did 2, now 3. The 3 goes in for the I, in the typical element, we get a 9. Then it increments to 4. 4 times 3 is 12. Then it increments to 5. We get 15. And because 5 is where we stop, we stop. And so we add that up. Whatever that is, it is represented by this summation expression. Summations do not have to have i's in them. They can start at values other than 1. So let's say k equals 3 to 6. And we'll have 1 plus k quantity squared. So that means the 3 starts into for the k. 1 plus 3 is 4. 4 squared, 16. Plus. Then it increments to 4. 4 plus 1 is 5 squared, 25. 5. 5 plus 1 is 6 squared is 36. And lastly 6. 6 plus 1 is 7 squared is 49. Alright, I didn't add all that up, but you're welcome to do it. Alright. The counters can also start at 0, and summations can have factorials in them, so go figure. 1 over I factorial. So if I start at 0, I get 1 over 0 factorial. 0 factorial is defined as equal to 1, just by definition. So we just have to accept that. And now this increments to 2, 1 over 2 factorial, plus 1 over 3 factorial, all the way up to 1 over 8 factorial. So by the time we get up to 8 factorial, it's a very small fraction. Alright, I'm not going to calculate that all out, but we might have to on an assignment. Alright, I'll end today with a special sequence which I alluded to way back here when I introduced the sequence 5, 8, 11, 14, 17. So 5, 8, 11, 14, and 17. It turns out some sequences can be quite obvious in that one term is related to the next by addition. So if I add something to get from here to here, and I add the same thing to get all the way through, not all sequences work like this, but when they do, they are special, and they're called arithmetic sequence. Looks like arithmetic, but is as an adjective, it's arithmetic. So the arithmetic sequence has this characteristic. It's one number is added to get the next, the same number is added to get the next, and so on. That number is called the common difference, because no matter where I find the difference between these two, any two numbers that are beside each other, they will always be common, the 3. 17 minus 14 is 3, 14 minus 11 is 3, and so on. Notice also this pattern. If I call the first term a sub 1, do you see the second term is a sub 1 plus the common difference? I'll call the common difference D because everyone else does. So the second term starts with the first term and you add the common difference. And the next one is a sub 1, it's this term plus another common difference, which is a sub 1 plus 2 common differences. The next one is this one plus another common difference. So then there'll be 3 of them. And so on. This one will be 4 common differences. So suppose we go all the way up to the nth term. So the nth term, I want a formula for the nth term in an arithmetic series. Arithmetic sequence. Well, we saw this pattern building. So if we are at the nth term, we know we're going to start with a sub 1 because all of our terms did. But how many common differences? Can you fill in? How many common differences would we count or use when we get to the nth term? So I'm going to put that number in here. Well, notice on the first term we didn't use any common differences, but on the second term we used 1 common difference. On the third we used 2. On the fourth, 3. On the fifth, 4. On the nth, how many? N minus 1. It's always 1 behind the number of terms. So this is a formula. It helps us get the nth term of any arithmetic sequence. A sub n equals a sub 1 plus n minus 1 times d. Alright. I think I'll leave that go for now, and that will be our lesson for tonight. We will be using this to help us find different terms in an arithmetic sequence. All right, that's all the jewels of wisdom for tonight. So guard them with your life. Till tomorrow. Bye.